Good day, class. So we will now continue with part 2 of our study of the origins of modern astronomy. So we will travel back in time and we will start our discussion with the contributions of the Greeks to modern astronomy. So come with me and let us travel back in time to the period of the Greek civilization. Okay, Scotty, beam me up. I said beam me up. Energize. Okay, class, so I'm back. So let's continue now with part 2 of our study of the origin of modern astronomy with the contributions of the Greeks. Now, the Greek astronomers, they were fond of using models to explain astronomical events or phenomena. So using models and their naked eye observations, the Greek astronomers were the first to use a careful and systematic manner to explain the workings of the heavens. So that's what they did. Plus the fact that the Greeks, they made use of logic and mathematics as tools for investigating the heavens. So unlike the Mesopotamians and the Egyptians, wherein they associated their study of the heavens with religion and superstition, the Greeks made use of models plus logic and mathematics to explain the workings of the heavens. Now, aside from using models plus logic and mathematics to explain the workings of the heavens, the Greek astronomers were also skilled in producing astronomical instruments. Now, one good example of an astronomical instrument that they developed was the astrolabe. Now, the astrolabe is an instrument used by the Greek astronomers to measure the altitude of the sun, the moon, the stars, and the planets. So we may consider this as a primitive sextant used by our seamen, by our navy, to measure the altitude of the sun, the moon, the stars, the planets. Okay, that's the astrolabe. Also, the ancient Greek astronomers developed this instrument. This was used by Eudoxus of Knidos. Now, this instrument was used by Eudoxus to simulate the ostensible motion of the planets. Eudoxus tried to simulate the motions of the planets using this instrument that he devised. So the ancient Greeks, they also constructed astronomical instruments to explain the workings of the heavens. Now, speaking of Eudoxus, Eudoxus came up with a model of a geocentric universe that was around 380 BC. Now, Eudoxus designed his model of the universe as a series of cosmic spheres containing the stars, the sun, and the moon, and they were all built around the earth at its center. So as you could see, class, Eudoxus came up with this model wherein the earth is at the center of the universe, or we call this the geocentric universe. Now, we usually associate the geocentric model with the name Claudius Ptolemy. Alright, but anyway, we will discuss later Claudius Ptolemy. So it was Eudoxus who came up with the first model of a geocentric universe wherein the earth is at the center of the universe. So this was his model of the universe wherein the earth is at the center of everything, and the sun and the 5 visible planets, they revolve around the central earth. Alright, class, so that's the model created by Eudoxus regarding the geocentric universe. Now, Eudoxus has a big problem regarding his model. Now, Eudoxus cannot explain the unusual movement of Mars. So, he cannot fit Mars in his geocentric model of the universe. So, that was the problem of Eudoxus. Now, Aristotle tried to develop his own model by improving or modifying the model made by Eudoxus. Aristotle borrowed from the idea of crystalline spheres from Eudoxus. The sun, the moon, and each of the planets have a crystalline sphere. The outermost sphere carried all the stars. So that was the model created by Aristotle. Alright, so again, this is just a modification of the model made by Eudoxus. He also placed the earth at the center of the universe, and the 5 visible planets, including the sun, they all revolve around the central earth. Okay, so the model made by Aristotle was just an improvised version of the model made by Eudoxus. And Aristotle also encountered the same problem. Now, Aristotle cannot explain the unusual movement of Mars. So, malaking problema ang kanilang na-encounter. They cannot explain the movement of Mars using their models. So as you could see here, class, the Greek astronomers, they made use of models to explain astronomical phenomena, and they also made use of logic and mathematics, plus the fact that they also produce astronomical instruments like the astrolabe. Now, the Greeks were skilled in the use of mathematics. Now, one good example to illustrate their expertise in mathematics was the contribution of Eratosthenes. Now, you will be fascinated by this, that Eratosthenes was able to calculate the circumference of the earth. And he did that even before Jesus was born. Fascinating, isn't it? So, this is how Eratosthenes was able to calculate the circumference of the earth. So, he heard about a famous well in the Egyptian city of Sagan on the Nile River. At noon, one day each year, that's the summer solstice, between June 20 and 22, the sun's rays shone straight down into the deep well. They illuminated only the water at the bottom, not the sides of the well as the other days, proving that the sun was directly overhead. Okay, so Eratosthenes made use of that well in Sagan in Egypt. Alright, so everybody, I want you now to zoom in on this illustration. So we have here this well in Sagan in Egypt. So between the days of June 20 and June 22, Eratosthenes would look into the well and he would notice that the bottom of the well is only illuminated and not the sides. So what does that mean? It means that the sun is directly overhead between the days of June 20 to June 22 in Sagan in Egypt. Alright, so to continue with the story of Eratosthenes. Now, Eratosthenes erected a pole in Alexandria, and on the summer solstice, he observed that it cast a shadow, proving that the sun was not directly overhead, but slightly south. Recognizing the curvature of the earth and knowing the distance between the two cities, Sagan and Alexandria, Eratosthenes was able to calculate the circumference of the earth. Fascinating, isn't it? See, very simple. You have that well in Sagan and that pole in Alexandria. That pole cast a shadow during the days between June 20 and June 22. And knowing the distance between the two cities, Eratosthenes was able to calculate the planet's circumference. Alright, so that's how skilled the Greeks in mathematics. Alright class, so before we continue, let's watch this fascinating video about how Eratosthenes was able to calculate the circumference of the earth. Now this is a segment from that video Cosmos by Carl Sagan. So let's watch this.
There was once a time when our little planet seemed immense, when it was the only world we could explore. Its true size was first worked out in a simple and ingenious way by a man who lived here in Egypt in the 3rd century BC. This tower may have been a communications tower, part of a network running along the North African coast by which signal bonfires were used to communicate messages of state. It also may have been used as a lighthouse, a navigational beacon for sailing ships out there in the Mediterranean Sea. It is about 50 kilometers west of what was once one of the great cities of the world, Alexandria. In Alexandria at that time, there lived a man named Eratosthenes. One of his envious contemporaries called him Beta, the second letter of the Greek alphabet, because he said Eratosthenes was second best in the world in everything. But it seems clear that in many fields, Eratosthenes was alpha. He was an astronomer, historian, geographer, philosopher, poet, theater critic, and mathematician. He was also the chief librarian of the great library of Alexandria. And one day, while reading a papyrus book in the library, he came upon a curious account. Far to the south, he read, at the frontier outpost of Sagan, something notable could be seen on the longest day of the year. On June 21st, the shadows of a temple column or a vertical stick would grow shorter as noon approached. And as the hours crept towards midday, the sun's rays would slither down the sides of a deep well, which on other days would remain in shadow. And then, precisely at noon, columns would cast no shadows, and the sun would shine directly down into the water of the well. At that moment, the sun was exactly overhead. It was an observation that someone else might easily have ignored. Sticks, shadows, reflections in wells, the position of the sun, simple everyday matters of what possible importance might they be. But Eratosthenes was a scientist, and his contemplation of these homely matters changed the world, in a way, made the world. Because Eratosthenes had the presence of mind to experiment, to actually ask whether, back here, near Alexandria, a stick cast a shadow near noon on June the 21st. And it turns out, sticks do. An overly skeptical person might have said that the report from Sagan was in error, but it's an absolutely straightforward observation. Why would anyone lie on such a trivial matter? Eratosthenes asked himself how it could be that at the same moment, a stick in Sagan would cast no shadow, and a stick in Alexandria, 800 kilometers to the north, would cast a very definite shadow. Here's a map of ancient Egypt. I've inserted two sticks, or obelisks, one up here in Alexandria and one down here in Sagan. Now, if at a certain moment each stick casts no shadow at all, that's perfectly easy to understand, provided the Earth is flat. If the shadow at Sagan is at a certain length, and the shadow at Alexandria is the same length, that also makes sense on a flat Earth. But how could it be, Eratosthenes asked, that at the same instant there was no shadow at Sagan and a very substantial shadow at Alexandria? The only answer was that the surface of the Earth is curved. Not only that, but the greater the curvature, the bigger the difference in the lengths of the shadows. The sun is so far away that its rays are parallel when they reach the Earth. Sticks at different angles to the sun's rays will cast shadows at different lengths. For the observed difference in the shadow lengths, the distance between Alexandria and Sagan had to be about 7 degrees along the surface of the Earth. By that I mean, if you imagine these sticks extending all the way down to the center of the Earth, they would there intersect at an angle of about 7 degrees. Well, 7 degrees is something like a 50th of the full circumference of the Earth, 360 degrees. Eratosthenes knew the distance between Alexandria and Sagan. He knew it was 800 kilometers. Why? Because he hired a man to pace out the entire distance so that he could perform the calculation I'm talking about. Now, 800 kilometers times 50 is 40,000 kilometers. So that must be the circumference of the Earth. That's how far it is to go once around the Earth. That's the right answer. Eratosthenes' only tools were sticks, eyes, feet, and brains, plus a zest for experiment. With those tools, he correctly deduced the circumference of the Earth to high precision, with an error of only a few percent. That's pretty good figuring for 2,200 years ago.
So that's how Eratosthenes was able to calculate the circumference of the Earth. Fascinating, isn't it? So just using that well in Sagan, and he erected a pole in Alexandria, and by knowing the distance between the two cities, Eratosthenes was able to calculate the circumference of the Earth. Alright, so just like Eudoxus and Aristotle, Claudius Ptolemy came up with a similar model of the universe by placing the Earth at the center and the Sun and the 5 visible planets, they revolve around the central Earth. So this is what we call the geocentric model made by Claudius Ptolemy, by placing the Earth at the center, the Sun and the 5 visible planets, they revolve around the central Earth. Okay, and just like Eudoxus and Aristotle, Ptolemy encountered a similar problem. Now, Claudius Ptolemy cannot explain the unusual movement of the planets, especially Mars. Ptolemy cannot explain the unusual movement of Mars. Now, what is so unusual about the movement of the planets? Now, everybody kindly take a look at this animated illustration. So you will notice typically a planet shifts slightly eastward from night to night, drifting slowly against the backdrop of stars. From time to time, however, a planet changes direction. For a few months, a planet heads back westward before turning back and resuming its easterly course. As you could see in this animated illustration, a planet moves from west to east. Then it goes back westward like so and turns around, going back to its easterly course. So this unusual movement of the planet, especially that of Mars, was observed by Eudoxus. This was also observed by Aristotle and by Ptolemy. So this westward motion of the planets is called retrograde motion. So here's another example. This is Mars. So you will notice in this animated illustration that Mars moves from west to east. Then Mars moves back westward like so, turns around and goes back to its easterly direction. Right? So fascinating, isn't it? So this was observed by Ptolemy, by Aristotle, and Eudoxus. So this is what we call retrograde motion of the planets. Now, what made the geocentric model of Ptolemy different from Eudoxus and Aristotle? Now, Ptolemy had introduced a unique solution to solve the problem of the retrograde motion of Mars and the other planets. So he introduced the concept of epicycles. Okay? So as the planet moves around the Earth, the planet also moves in a circular motion. It is like a smaller wheel turning around a larger wheel. Okay? So let's take a look at this animated illustration. So the blue dot represents planet Earth. So the Earth is at the center, and the red dot is the planet Mars. So as Mars moves around the Earth, Mars also moves in a circular motion. So again, a smaller wheel. Look at the movement of Mars. That's the smaller wheel turning around a larger wheel. That's the orbit of Mars around the Earth. Right? And that's how Ptolemy had solved the problem of the retrograde motion of Mars and the other planets. Okay? So the Earth is at the center. That's the green dot. And the red dot is planet Mars. So as Mars moves around the Earth, Mars also moves in a circular motion. Smaller wheel turning around a larger wheel. Okay? So that's how Ptolemy had solved the problem of the retrograde motion of the planets, especially Mars. So he introduced the concept of epicycles. Okay? So fascinating, isn't it? Okay, so the inclusion of epicycles in the geocentric model of Ptolemy had solved the problem of retrograde motion of Mars and the other planets. And this has become the standard model of the universe. The inclusion of the epicycles had solved the problem of retrograde motion, and this has become the standard model of the universe. So the Catholic Church had accepted this model. This has become the standard model of the universe.
The ancient Greeks provided more detailed information about our dominant celestial neighbors, the sun and moon.
Even back then, 2,000 years ago, they knew that the Earth curves. And by looking at the shadows, they calculated the size of the Earth to within about 10% accuracy. They actually calculated the distance from the Earth to the moon and the rough dimensions of the distance from the Earth to the sun. So in other words, the ancients were no fools.
The ancient Greeks also recognized two types of stars. Most were fixed and small and moved together. A few were larger and moved haphazardly, or so it seemed. These were planets, and predicting their motion became a centuries-long goal. With just their naked eyes to scan the skies, the Greeks saw only 5 planets, naming each after their gods. Today, we're more familiar with their Roman designations: Mercury, Venus, Mars, Saturn, Jupiter. Ancient astronomy assumed a concept of the universe proposed by 4th century BC Greek philosopher Aristotle, who imagined the Earth at the center of the universe, with the sun, moon, stars, and planets all revolving elegantly around it in perfect crystalline spheres.
Aristotle's universe was finite. It was a big sphere. Actually, it was like onion. It was an onion with many concentric spheres.
1st century astronomer Ptolemy improved on Aristotle by accurately tracing the paths of the planets, which didn't move haphazardly after all. Using complex circular motions called epicycles, Ptolemy could predict their prescribed paths and changing velocities. In other words, Ptolemy's system reliably predicted the future behavior of the planets, another step in man's journey to understand and control the universe.
The Ptolemaic system was extremely complex. It had all these planets going in loops, and it worked beautifully, but it was just wrong. The idea that you can predict something doesn't mean you understand the fundamental principles behind it.
Ptolemy's system did not accurately reveal the universe, but it didn't try.
He essentially showed that the positions of the planets could be calculated for any time past or future. It was a tour de force of mathematical understanding. Interestingly, the astronomy seemed to stand still for centuries after that.
In fact, after the collapse of Rome in 476 AD, astronomy actually lost ground.
Europe fragmented into smaller powers, and a lot of the wisdom of the Greeks was lost.
1,000 years later, a new theory would confront accepted beliefs about how the heavens worked and would move mankind one step closer to a theory of the Big Bang.
Now, this geocentric model of Ptolemy was accepted for several centuries, until an astronomer by the name of Nicolas Copernicus came up with another model of the solar system of the universe by placing the sun at the center. Copernicus formulated a model of the universe that placed the sun at the center of the universe rather than the earth at the center. Okay? So we know this now as the heliocentric model of the universe. So Copernicus had placed the sun rather than the earth at the center of the universe. So we call this the heliocentric model. Helio meaning sun, sun-centered model of the universe. Now, using this heliocentric model, Nicolas Copernicus was able to solve the problem of retrograde motion of the planet, especially that of Mars. Now, according to Nicolas Copernicus, retrograde motion occurs roughly when a faster moving planet catches up to and passes a slower moving planet. Now everybody, I want you to zoom in on this animated illustration. Now the blue dot represents Earth and the red dot represents Mars. Now we know for a fact that the Earth moves around the Sun faster as compared to Mars, as Mars is a slower moving planet. So as the Earth passes Mars, we see here from our perspective here on Earth that Mars moves in a retrograde motion with respect to the background of stars. Fascinating, isn't it? So that's how Nicolas Copernicus explained retrograde motion of the planets, especially that of Mars, using his heliocentric model. So retrograde motion, according to Nicolas Copernicus, occurs when a faster moving planet like planet Earth catches up to and passes a slower moving planet like Mars. So we see here from our perspective here on Earth that Mars moves in a retrograde motion.
The first to suggest a heliocentric model since the time of Aristarchus was a Polish man named Copernicus. He demonstrated with great precision that all of the problems with the geocentric model instantly vanished if the Sun is placed at the center of the solar system. Objects closer to the Sun orbit faster, and the retrograde motion of a planet like Mars is now simply the result of Earth overtaking Mars at a particular time in their respective orbits. As we pass by Mars with a greater angular velocity, there is a moment where it appears to move backwards, just like when you pass a car on the highway and it appears to you to be moving backwards, given its slower velocity. Copernicus even estimated the distances from the Sun to each planet with great precision, using some ingenious geometric calculations. But there were still some issues to iron out. Critics of the heliocentric model had one very valid point. If the Earth goes around the Sun, the apparent position of the stars should shift. It would be several hundred years before we had telescopes powerful enough to see it, but this shift does indeed occur. It is just incredibly small because of the staggering distances to the stars. We use this slight shift today to measure the distance to certain objects in space. To understand why this works, hold a finger in front of your eyes. Then alternately open and close one eye at a time. Your finger will shift left and right depending on which eye is looking at it, because your line of sight is originating from a different location. Keep doing this as you move your finger away from your face. The shift in location becomes less pronounced with greater distance. If you try this with an object across the room, it already starts to be relatively negligible. Now imagine that the Earth being on one side of the Sun is your right eye, and the Earth being on the other side of the Sun is your left eye. A distant star will change its position in the sky, just like your finger, but the star is so far away that we need mechanically precise machines to measure the apparent shift.
Now, you will notice in the explanation provided by Nicolas Copernicus in explaining the retrograde motion of the planet, especially that of Mars, he eliminated the use of epicycles. he never mentioned anything about epicycles in his heliocentric model. So, in a way, Nicolas Copernicus had contradicted Claudius Ptolemy by eliminating epicycles. Now, we know before that Claudius Ptolemy had introduced epicycles in explaining the retrograde motion of the planet, especially that of Mars, in his geocentric model. So, Nicolas Copernicus, using the heliocentric model, helped explain the retrograde motion of the planet, especially that of Mars. And he contradicted, by eliminating epicycles, he contradicted Claudius Ptolemy. Okay? Alright, and Nicolas Copernicus came up with his book entitled On the Revolutions of the Heavenly Spheres. And by eliminating the use of epicycles in his model and contradicting Claudius Ptolemy, the church did eventually ban the book in 1616. Alright, so that's a very interesting story of Nicolas Copernicus. And by contradicting Claudius Ptolemy, by eliminating the epicycles concept, his book was banned in 1616. So this was the book written by Nicolas Copernicus on the revolution of the heavenly spheres. And in this book, Nicolas Copernicus also provided the explanation on the retrograde motion of the planets, especially that of Mars. So, before we continue, let's watch this fascinating video.
Ptolemy believed that the Earth was at the center of the universe, that the sun and the moon and the planets like Mars went around the Earth. It's the most natural idea in the world. The Earth seems steady, solid, immobile, while we can see the heavenly bodies rising and setting every day. But then, how explain the loop-the-loop motion of the planets in the sky, Mars, for example? This little machine shows Ptolemy's model. The planets were imagined to go around the Earth, attached to perfect crystal spheres, but not attached directly to the spheres, but indirectly through a kind of off-center wheel. The sphere turns, the little wheel rotates, and as seen from the Earth, Mars does its loop-the-loop. This model permitted reasonably accurate predictions of planetary motion, where a planet would be on a given day. Certainly good enough predictions for the precision of measurement in Ptolemy's time and much later. Supported by the Church through the Dark Ages, Ptolemy's model effectively prevented the advance of astronomy for 1,500 years. Finally, in 1543, a quite different explanation of the apparent motion of the planets was published by a Polish cleric named Nicolas Copernicus. Its most daring feature was the proposition that the sun, not the Earth, was at the center of the universe. The Earth was demoted to just one of the planets. The retrograde or loop-the-loop motion happens as the Earth overtakes Mars in its orbit. You can see that from the standpoint of the Earth, Mars is now going slightly backwards, and now it is going in its original direction. This Copernican model worked at least as well as Ptolemy's crystal spheres. But it annoyed an awful lot of people. The Catholic Church later put Copernicus's work on its list of forbidden books. And Martin Luther described Copernicus in these words. He said, "People give ear to an upstart astrologer. This fool wishes to reverse the entire science of astronomy." Close quote.